Hello and welcome to another one of D's ADD videos. Today we're going to be looking at the concept of waves, part 1. Part 2 will deal with the orbitals. So, what is a wave? Well, waves are oscillations that move outward from a disturbance. Okay? There's two types. There's standing and traveling waves. And basically, the standing waves, we'll talk about this again later. The peaks and troughs do not move horizontally. That would be like a guitar string. And a traveling wave would be like a wave in the ocean where the peaks and the troughs move horizontally. And most of you have dealt with waves in math. You know that the amplitude is going to be the distance to the peak or the distance to the trough. You know that there's frequencies telling you how many times it comes along per second, number of cycles per second. Frequencies measured in hertz. We have 1 hertz is equal to a second inverse. Then the wavelength is the peak to peak distance or trough to trough distance. Now this is a mistake. I'm going to highlight this in pink. This should not be velocity, this should be frequency. I apologize for that we will have the handout corrected ASAP. But right now what I have to work with is this handout, so we're going to go with what we have. Change this again to frequency. So it's frequency is the speed of light over the wavelength. The speed of light is generally agreed to be this is of course rounded off, as 3 times 10 to the 8th meters per second. This 8 right there is a exponent, so it's 3 times 10 to the 8th raised. All right. So the electromagnetic spectrum is the spectrum of frequencies that we deal with on a day-to-day basis. So there's everything from microwaves, radio waves, our visible spectrum that allows us to see, and the rest of the radiation. And it basically looks like this here. Okay, so you can see that our visible range is just a narrow slit, okay, that roughly is between 400 nanometers to 800 nanometers. All right. Roy G. Biv is the color scheme, so I guess these colors are a little bit out of whack. No, I guess that's right. All the other ones are the same way. It should be backwards. Yeah, no, this one is out of whack. Let's try another one. Okay, we're going to stop this. So here is our electromagnetic spectrum. As you can see, we have gamma rays, X-rays, ultraviolet, and all these other rays, but the very, very, very narrow range of 400 on the violet region of the spectrum, visible light spectrum, to the 700, which is the red portion. Okay, so basically, our visual spectrum is a very narrow sliver of what's actually out there, wavelength-wise. So, back to what we have here. We should be able to look at infrared absorption spectra of different elements and basically come up with its own fingerprint for these elements. Okay? The tiny packets that we refer to as photons of light can be basically calculated their energy by using Planck's equation here. Max Planck, a physicist, came along and said, yeah, we have photons, these tiny packets of energy that we need to look at, and we use Planck's constant, and again this should be not velocity but frequency, and Planck's constant I believe is 6.626 times 10 to the negative 34 joule seconds. Okay, and this would be the energy associated with that quanta or that packet of So each one of these elements has its own characteristic absorption spectra. Okay, if we were to excite it, whatever element we're looking at as a gas, and give off the discharge electrically, they fluoresce and they give off energy, and they give off distinct color bands of light when we put it through a prism. And this can help identify each element. Okay, so for instance, if you were to look at the absorption spectra for sodium, you would see a blue line roughly at 500 nanometers and a orangish line just above 650 nanometers. Oh, I'm sorry, that's hydrogen. Whereas if it was sodium, you would see a couple lines next to each other just below 600 nanometers. Okay, so each one of these has its own fingerprint when it comes to atomic spectra. So here we have the Rydberg equation, and what Rydberg equation does is it allows us to calculate the individual wavelengths for just the hydrogen atom absorption or atomic spectra. Okay, so if we were to look at the lines, the blue line at just below 500, and the orangish red line just above 650 on the atomic spectra of hydrogen, and you wanted to calculate the wavelength, you would use this. N1 is the ground state, N2 is the excited state, and RH is Rydberg's constant, which is right here. And you can just plug and chug some numbers. All right? Okay. Then Niels Bohr came along and looked at it from a point of view of just energy and the energy levels they're at. And what he did was he was able to quantify this energy by using this constant over the quantum number that you're on, or the row that you're on. That constant is given to you right here. And basically, whenever they fluoresce these electrons, they go from one shell to the excited shell to the native shell, and they give off energy. And this equation can give you that energy. Okay, so it's basically B is a constant that's made up of the Planck's constant, the charge on the electron, the quantum numbers, a bunch of other stuff, but it's just easier to memorize this constant. All right, so then if you had two levels, you could calculate the difference in the energy levels by just doing minus B, and then you would do the difference in the reciprocal of the quantum numbers. Okay, and that would look something like this equation here. Let's see if we can write that down. So if we did delta E, that would equal the native state minus the excited state no, I did that backwards. This would be the lower energy level. Sorry, it's 2 o'clock in the morning, I'm tired. So the lower energy level, this would be the higher energy level. My marker's a little too thick. Let's make that smaller, about half the size. And if we were to use the equations there, it would be minus B over NH squared minus A minus B over NL squared. So delta E would then equal B over 1 over N, the lower energy level, minus the higher energy level. That's leaving the negative sign in there, squared. Okay. If you remember, we can also use the Planck's constant equation for energy. If you don't remember, let me just go through it real quick with you. Oops, different color is what I wanted. So if we were to look at this is frequency, which then if we use the lambda times frequency equals the speed of light equation. Solve for frequency, we get c over lambda here, and then we can plug that in for the energy. So if I do that, we had E right there, right? So we can do hc over lambda, and then if you divide both sides by hc, you get 1 over, let me do this a different color because this is the final main equation I was trying to get to. So you would get, oh, so much for a different color, take 2. 1 over lambda equals b over hc. This is just multiplying by 1 over hc on both sides. The lower energy level minus the higher energy level. Okay? So we have a way to say that would be the n sub h level must be greater than the n sub l. All right? So that's basically Bohr model, but the problem is if we have more than one electron, this fails. Okay? So there is another equation that deals with wavelength that de Broglie came up with, and de Broglie's equation states that lambda, this is de Broglie, this equation equals h over mv. Now this v actually is velocity. Up until now that v has been what? Frequency. And you might ask why they did that. I ask the same question quite often. But here we're talking about wavelength. This is Planck's constant. This is the mass. And this is the velocity. So another way to obtain wavelength given different types of information. All right, oops, sorry about that. Let's rotate that back. Whoa. That's basically it for the fundamentals of waves. There are, we already talked about standing versus traveling waves in the sense that standing waves, the peak and trough do not move horizontally, whereas the traveling waves do. There's diffraction. Basically, whenever waves can combine constructively and boost each other, or destructively and interfere with each other. All right, so I just wanted to go over some of that terminology. And yeah, the rest of that has to do with orbitals, so check out the orbitals video. But you should be able to use any of these equations with as math problems. Basically, you'll be given pieces of the puzzle and asked to change. Make sure your units are right. If your stuff is given to you in centimeters, make sure you convert to meters, and so forth and so on, or use the right units for the speed of light. Again, both of those velocities in the first two equations should be frequencies. I apologize for that. Planck's constant, 6.63 times 10 to the negative 34 joules second, and that's basically it. Okay, so make sure you watch example videos where I'll do a few calculations of each of these. Practice, practice, practice. As always, the most important part of all this. And thank you and have a nice day.